Good afternoon. This is lecture 19, module 3, basic matrix concepts. We are doing the third lecture in this third module. If you recall, we have just started the second topic of introduction to matrix structural analysis. This is covered in chapters 2 and 3 in the book on advanced structural analysis. We had covered the introduction, basic coordinate systems, and in this session we will look at the transformation matrices and stiffness matrix. This is to refresh your memory. Please see what the real task for us is. We want to be able to make the digital computer do structural analysis. We want first of all to have a framework in which we show the structure geometrically, which means we have to identify the elements, the nodes with reference to some Cartesian coordinates. We have to identify the active degrees of freedom, restrained degrees of freedom, and that is how we define the vectors D and F. D is the displacement vector, F is the force vector. The subscript A stands for actions if you are referring to forces, and it stands also for active degree of freedom if you are referring to displacements. So FA, the submatrix FA really is a load vector, and FR is a reaction vector. R stands for reactions. R also stands for the restrained degree of freedom. So dr is the restrained displacements. The displacements are usually 0 unless you have some known specified support settlement. Next, you will recall we defined the local axis. In this particular plane frame example, you have 3 elements and we have the local coordinates, the local axes. You have 6 degrees of freedom per element. So you have the element displacement vector, the element force vector, and we use some superscripts and subscripts to clarify. You remember the star is what we use when we want to refer to the local system, and in the superscript we put I referring to the ith element. So here I can be 1, 2 or 3, and you have 6 different displacements and 6 different forces, and we can assemble all the elements together into one overall combined element displacement vector D star. In this case, what will be the size of D star? 18 by 1, because D1 star itself is 6 by 1, D2 star is 6 by 1, D3 star is 6 by 1. So this is convenient to do when you are dealing with small frames. When it is a large frame, we do not do this. And similarly, you have F star. Now let us look at transformation matrices. You need to know how to switch between the structure and the element. So you have some relationships. This is a linear transformation. So you can transform from Di to Di star. So this is a standard transformation. Ti is called the transformation matrix, the element transformation matrix, and the same Ti holds good not only for displacements but also for forces. This is the conventional stiffness method, and the interesting thing about the transformation matrix is that it's an orthogonal matrix which has this beautiful property of the inverse being equal to the transpose. So it is very easy to do the reverse switch, that is you can move from the local coordinates to the global coordinates, and we will see how this can be applied. So this is one major type of transformation we do. You would have studied in school coordinate geometry, so you know about what happens when you shift the axes, you rotate the axes and so on. So it is something similar. There is another set of transformation we will see later, where you can do what is called a displacement transformation matrix. This is used especially in the reduced element stiffness matrix. We will see this later. This can also be applied to the conventional stiffness matrix. When you do the flexibility method, you have the force transformation matrix. You can do the switch from the global to the local coordinate. So we will see these as we go along. You will find that with increasing familiarity you will understand everything, but it is good to plant the seeds early. We will keep coming back to these slides and your understanding will get strengthened. Okay, so you can work both from global to local and from local to global. Just to give you a big picture view of the different methods we are going to study, the so called conventional stiffness method is the way softwares work in computers. Okay, this is how it is done by the computer. This is a master method, very generic, dealing with slightly big matrices. I am not sure if this is what is taught in many Indian universities in matrix methods, because what is taught is the simplified version of it, which is more convenient to do manually. So we are going to refer to that as the reduced element stiffness method. It is equally accurate, but here you have less flexibility. It has some limitations, and here you deal with smaller size stiffness matrices. The number of degrees of freedom are less. We will discuss this in the next class, and the stiffness matrix you get here has an inverse, and that turns out to be the flexibility matrix. So you have the third method that we need to study. It is called the flexibility method. In software packages you do not have the reduced element stiffness method, you do not have the flexibility method. So in many advanced courses they do not waste time with these methods, they just cover the conventional stiffness method. In fact, many modern textbooks do only that. Traditional textbooks cover everything, but sometimes in many universities, I think in your GATE exam for example, they will cover the reduced element stiffness method without calling it so. They will still call it a stiffness matrix method, but it is actually the reduced version of the method, and you learn flexibility method. What we are trying to do in this course is to cover everything, but for manual use, to demonstrate in the class and so on, it is probably easier to use the reduced element stiffness method compared to, but we will do both, because we would like to know how the black box in the computer works. So you should see the big picture. So we begin with the Wright Royal conventional stiffness method. So let us take a fresh look at this conventional stiffness method. The global, you can express the degrees of freedom both along the local axis, which is what we saw earlier, but you can also do it along the global axis. So for example 1, 2, 3, instead of pointing towards the local longitudinal axis 1, we can point towards the global x axis. Can you see that? So this is a big change. That means we do the transformation here itself. So I am not putting the star anymore. Remember 1 star, 2 star, 3 star, there the 1 was pointing along x star this way, 1 was along that, 2 was normal to it. Now 1 is parallel to the global 1 and 2 is parallel to the global y axis, and you will find the 3 does not change. Why does not the 3 change? Yeah, because the vector pointing outward from the xy plane is the same, so that does not change, so there is no transformation needed there. So it is like you do the correction at this stage itself at the element level. If you can define 1, 2, 3 like this, you can also define 4, 5, 6, and similarly for all the 3 elements. Got it? So this is another way of doing it. This is the transformation that we are trying to do, and so I am now defining element displacement vectors and element force vectors. They are still element because the I comes here, I refers to the ith element. So this is for I equal to 1, 2, 3. The big difference between this and the previous element displacement and force vectors is how in designation how do I make the difference? That star is missing, okay, the asterisk is missing. Have you understood? Now all we need to know is how to switch from the local axis system to the global axis system, and then the job is done. Okay, how do we do that? Let us take a look. Let me explain once more, and please listen carefully, pay attention. This is what we did in the last class, right? Here you have 1 star, 2 stars, 3 star and so on, 1 star, 2 star here for sure. If this joint has moved here, the displacement along the local x axis is d1 star, right, with the I stands for the ith element, and this movement normal to it is d2 star, is it clear? And this change in angle anti-clockwise is d3 star. Does this make sense? You are clear about the physical meanings of, and similarly I can define d4 star, d5 star, d6 star. Is this clear to all of us? Mind you, this theta I that I am talking about here is not referring to a displacement, it is referring to the original inclination of the member prior to loading with reference to the global x axis. Is that clear? So this is what we mean by the local axis system. What do we mean by the global axis system? Okay, this is a similar representation of the element end forces. Do you understand this now? Now if I have a force acting this way, I call it Fi2 star. Along the longitudinal x star axis, I call it Fi1 star. A moment acting this way, I call Fi3 star. These three are conjugate with these three. Can you see that? The directions are the same. One are a set of forces, the other are a set of displacements. The same here at the other end. This is the end node, this is the start node. Does it make sense to you? So this kind of description of element level forces is what we call the local axis description. We have another description, the global axis. Let us see how that looks. Now I am taking the same element and I am taking the same displaced configuration, but I am choosing to define the displacement d1 as parallel to the x axis, do you see, and di2 as parallel to the y axis, and d3i does not change, it is the same as d3i star. These two do not change, you can see there is no change, but these two change. Likewise here this moves horizontally d4i, d5 and this is d6. Doesn't, do you get the hang of it? Similarly here the component of the force along the x axis, global x axis, if F1, along the y axis global y is F2 and the moment is F3, F4, F5, F6. Does this make clear? So with this graphically I am trying to show you what we mean by defining the element vector, displacement vector, force vector. You have two choices, one with a star which tells you have to align yourself along the longitudinal x star axis, the other one is you align yourself along with the global x axis. Is it clear? Now there is a relationship between these displacements and they are defined this way. The boss here is central government, that means the global axis is your foundation and from that you switch to the local axis, and you do it through a transformation, a linear transformation using a matrix, a standard matrix called the TI matrix. It is a transformation matrix. Can you work out a relationship of this matrix? What is the size of this matrix?
2 by 2. 3 by 3.
2 by 2.
Why 2 by 2 and 3 called? Okay.
Wait, let's
that
show
was
me 2 by
changed.
2 only.
You have to understand the question first. What's the size of this for the ith element?
6 by 1.
6.
There are 6 degrees of freedom. You are right, the 3 comes from one end, but the element has 2 ends. You have a head and a tail. And what we are saying is this you get by transforming, and this is a transformation matrix, you are transforming something else. What are you transforming? Ti.
That is also 6
This is
by
also 6 by 1. This matrix is a transformation matrix which I call Ti. Obviously this has to be 6 by 6.
DI से DI star.
But there is some nice property about this matrix. What's a nice property? Apart from that, this matrix will look like this, right? Even this you can partition, this you can partition. This belongs to the start node, this belongs to the end node. Because you are following a stiffness formulation, will there be any relationship between this and this? They are independent. Actually, this is independent with this, and this whole thing is independent with these. So you will get some zeros somewhere here, no? So which will be zeros? Yeah, so the off diagonal matrices will be null matrices, right? And whatever relationship you get here, let's say this is A, this will also be A, right? Does it make sense? Okay, let me explain. You got 3 by 3 here. Now this is related to this through this transformation, right? This will be related to this through a similar transformation, isn't it? Does it make sense? Yeah, but once you have a transformation, they are not independent. These two are dependent. These two are dependent. What is their dependence? This transformation. You are just rotating the axes. Obviously there is a dependence, right? Can you tell me what A will look like? There you are, it's a function of direction cosine. It's not difficult to work out. So it will look like this.
In DI star, the first 3 elements will be identical to the next 3 elements. I mean, they are pointing in the same direction.
I don't get what is this?
X star in the same direction along the element, entire element.
Along the longitudinal axis of the element you have, that's the axis X star. The displacement at any point along the element will vary. The displacement at the extreme left end is our unknown, we are calling that D1 star, and at the end node we are calling it as D4 star. D1 star and D4 star are independent. That is why we call them degrees of freedom. Any pending doubts? You will get the hang of it soon. This is quite straightforward. Have you got it? So this is your A matrix and it is easy to establish. Now take a look at these relationships. This is exactly the relationship we wrote there. This is the fundamental transformation matrix used in the conventional stiffness method. It is very easy to remember. You have a cosine and you have a sine. Everything is positive except the second element for obvious reasons. So you have cos theta and minus sine theta. Why is it minus sine theta? Because it goes to the negative side. I hope you can work this out, this is straightforward. We will do it in great detail when we get into the actual problems. So do we get this? This is our A matrix, this is for the start node, this is for the end node. Everything is same except that 1, 2, 3 gets replaced by 4, 5, 6. Does it make sense? So if you want to put it all together, it will look like this. Clear? Standard transformation. Okay. The property about this is it is an orthogonal matrix. Now, why did we align 1 star, 2 star, 3 star along the global x, y and z axis? Why did we make it 1, 2, 3? What do we achieve by that? What do we achieve by that?
So you can span
Think
the
in
entire
terms
vector
of
space.
displacements. There,
Span any displacement or the entire vector space will be spanned by that.
that you can span even with the local coordinates. Let me give you a clue. First we began with a structure. In that particular frame, how many displacements we had? We had 12, dA and dR, right? We had d1, d2, d3 all the way to d8, they were active degrees of freedom, d9, d10, d11, d12 were restrained degrees of freedom. How are those linked with these? How are those linked?
Maybe by flexibility.
So you have to think in the stiffness language. In the displacement methods, what is fundamental? Displacements. Okay, displacements are fundamental. And how do you link the state government with the central government? How do you link the element displacement with the structure displacement?
When
This is very important. It's very simple. Remember, this was our first element, this was our second element, and this was our third element, right? And the structure was kind of fixed here, had a roller here. So let's look at the active degrees of freedom. If you remember, okay, why don't I join them? This was element 1, 2 and 3. What were our degrees of freedom? We said this joint, we start the active degree numbering here. We said this is 1, this is 2, this is 3. Remember? This is for the structure. Now, what is D1 equal to from the element point of view? How will I write it? See, you now know all the definitions. It is exactly equal to D first element, this element. There you go. Very nice.
4, yeah.
Needs little thing. Plus? Plus?
That's it, sir.
Wait. This element moves here. This element moves here. This joint also moves there. Where is the plus coming? So you have to get out of statics where you do plus to kinematics where you don't do plus. A conjugal relationship, say between husband and wife, works as long as there is no separation. So don't separate out. So this is compatibility. Do you get it? In defining these these displacements itself, you are defining compatibility. What is this equal to for the second element? Now you got the hang of it. So that's why we are playing this game. You must see there's a big difference between trying to figure out what somebody else worked out and trying to figuring it out yourself from first principles. So let us say you had to find a way to make the computer do it. It's wonderful. Go ahead, let's continue. What is D2? Somebody else tell me from this side, what is D2 equal to?
D1
D1 5 D2
that is the
what is D3 equal to?
D1 6 D2 3
Equal to?
2 3 3 What is 3? 3 sir, that is 3
You're getting the hang of it, right? And so on and so forth, we won't waste our time. So this was 4, 5, 6, etc., etc. Got it? That's the idea. The idea is you do the correction early stage, then you are satisfying compatibility straight away. Okay. So these are the fundamental transformations. The element transformation matrix Ti is a square orthogonal matrix which enables member end displacements and forces expressed in a global axis framework to be transformed to the local axis system. Transformation from the local axis system to the global axis is enabled by the transpose of this matrix which is equal to the inverse of the matrix. Okay, you can switch back and forth. Let us give an example. Okay, this is a pin jointed truss, pin jointed frame. How many active degrees of freedom do you think there are? It's a plain truss. 3. It's a truss.
2.
2 sir.
Where can you apply loads? Only at O. A, B, C, D are all supports. So 2 active degrees of freedom. These are coordinates 1 and 2, right? One along the global x and one along the global y. Then what are how many restrained degrees of freedom do you have?
1 2 3 4
4 sir. 4 sir. 4.
Why do you say 4?
Because it is along the member force acts. So for each member only one at A1, B1, C1, D1.
But he is strictly right in the sense you know the direction of your support reactions in this case, because they have to be aligned along the members in this particular problem. But if they say it, you let go a little bit, doesn't matter, it's okay, you will finally get the same answer. So don't be too rigid, let us accept what they say, let us say 3, 4, 5, 6, 7, 8, 9, 10, but we know that the reactions are not independent, but then you are bringing equilibrium. I am doing stiffness method, I know only compatibility, until I bring in equilibrium I cannot say that okay, that the reactions are related. So let us leave it like that, right, this is fine. What about our element? All 4 elements I reduce to one element, because why should I draw 4 pictures? I like drawing one picture, and all 4 I cover with an angle theta xi, and if the length were this height of that truss is L, I can write an expression for the length of all 4 members as L divided by sine theta. Got it? I need 4 values of theta, they come from that truss, these are those 4 values. Okay, I am measuring with respect to the positive x axis, got it? Now I want to generate, ultimately I want to generate the stiffness matrix, but let us begin with the transformation matrices. So my local coordinates are 1 star, 2 star, 3 star and 4 star, got it? And 1, 2, 3, 4 is like this without the star. 1, 2, 3, 4 is along the global axis system, 1 star, 2 star, 3 star, 4 star is along the local axis system. By now you know. Now how do I write the transformation matrix? Is it clear till now? I am doing it I have taken a very simple example. How do I do it? Well, I also have the stiffness, let us say. Does this make sense? It is the same A matrix we got there without the rotation component, which is 1. So you have cos theta minus sin theta cos theta. Does this make sense? Okay, this transformation is straightforward. Again, off diagonal is null submatrix. Is it clear? Okay, let us apply it. No doubts. So we have done an example of a plane frame transformation, and we are doing it in a plane truss. You can do a beam later. Fine. How do we proceed? Now this is important. The size of this matrix is 4 by 4. There are 4 elements for each of them. So there are 4 transformation matrices, and for each of them it is 4 by 4, right. So if you take, for example, this element 2, okay, we want to fill here and here, but we can straight away mark the linking what? Global coordinates. See, we have identified this element is 1 2 and it is matching with this 1 2 and this is 3 4, but for the global coordinates this is not 3 4, this is 5 6. Are you getting what I am saying? So let us write to help you understand what we are doing. For that particular problem, this is 5 6, this is 1 2, right. This is global coordinates. This is 1 2 3 4. What is this? This is local coordinates along global axes. That means I have already aligned it in this direction, right. Now D5 and D6 in the structure must be equal to, how do I write that D4? Like the same way we wrote here. For this second element 2, how should I write that? In that second element, D2 4. Now I do not write so much for convenience. I do it in brackets here, the parentheses here. You get it? 1 2 3 4 is local. 1 2 3 4 this way, so it is 1 2 5 6 global coordinate. This is helpful for me. This is a clue for me that the displacements that I get at the element level are the same as the displacements I get at the global. No plus here, be careful, it is exactly equal. So it helps me assemble my structure stiffness matrix from my element stiffness. Is this picture clear to you? So like this you have to play a game, and you can similarly take for T1, T2, T3, T4, right. And I need to plug in the empty boxes. How do I fill in those empty boxes? Sine, cos, that is easy to do in a tabular format, I can do it effortlessly. Is this clear? So let us go through this once more. For element 1, 1 2 3 4 are the connecting start and end nodes, right. 1 2 3 4 1 2 3 4. For element 2 we have already finished. For element 3 it is 1 2 7 8 1 2 7 8 which match with the local coordinates 1 2 3 4, and for element 4 it is 1 2 9 10. Does this make sense? Okay. Now you can do this neatly in a tabular fashion. Mark your start node, mark your end node, mark the theta value, calculate cos theta and sin theta, which are also called direction cosines. Get the length, in this case it is also a function of sine, and just plug in those values, cos theta, sin theta and all that. So you understand, all this is very easy to do, it is mechanical, the computer will do it effortlessly, MATLAB you can do it easily. So that is how you generate what? Generate transformation matrices. Now we look at stiffness matrix. We already know the definition. Kij, it is called the stiffness coefficient, is the force Fi generated at the coordinate I on account of a unit displacement dj equal to 1 at the coordinate j with all other degrees of freedom restrained. You are very familiar with this definition. In matrix forms, it looks like this in the local coordinate system, and this for each element. For the ith element it will look like this, and for the entire structure it will look like this. Got it? For each element it will look like this, for the entire structure it will look like this. Here you do not have a star, you do not have I, because all the elements contribute to this matrix. This is for an individual element. Is this clear? Okay. Now let us look at typical elements that you may get. Let us keep it simple. So we look at a plane frame element, 6 degrees of freedom, we have already done that. Plane truss element, how many degrees of freedom? 4 degrees.
4.
Right? 1, 2, 3, 4. Because you can have 4 different displacements. And a beam element, we assume that actually does not move, so you have only a translation, a deflection and a rotation, 4 degrees of freedom. Got it? 1, 2, 3, 4. We will keep looking at these 3 elements again and again. Okay. Obviously the plane frame is the most generic because it is a combination of the beam and the truss. It is a combination of beam and the truss. Okay. Now the stiffness matrix for a plane frame element will look like this. Let us not fill in those, but you know the meaning of this. It is a 6 by 6 matrix. Okay, it is relating Fi 1 star to 6 star to Di 1 star to 6 star. It is a 6 by 6 matrix. It is going to be a symmetric matrix, it is a square matrix. And how do you fill these? You already know a physical approach. You can give one displacement, arrest the others, you can fill this up, but you can also do it using many other techniques including the energy method. We will see all this later. I am just introducing notation, I am giving you a framework how to do matrix analysis. Let us take one example, something you have never seen till now. I want you to generate right here, right now, in the midst of your yawning at 5:30 after doing a lab. I want you to wake up and generate the 4 by 4 stiffness matrix for a truss element, all of you. How to do this? It is going to look like this, it is going to be symmetric, generated. By the physical approach, that means you do not need any calculations. Okay. So what is the first thing you will do? You have to draw a sketch where you apply only one unit displacement. Which one will you apply? So d1 star equal to 1. Can you draw a sketch? It will look like this. You just have to push it horizontally. You have an element d1 and all the others are restrained, right? What is the force you need to push it? Ea by L, actual stiffness. What is the reaction you will get at the other end? With a negative sign. Why? Because it has to be opposite. We have chosen 3 star positive, right? Now what is K2 star 1 star? You see this symbol, does this make sense to you? We have got this value, that is Ea by L. We have got this value which is minus Ea by L. What is this value and what is that? Why is it 0?
Because no reaction is
there is no resistance, if there is no reaction there is no problem, right? So those are 0, correct, those are 0. Next sketch is going to be tricky. Now you apply d2 equal to 1, d2 star equal, draw it like what? Draw it. Give me the 4 values. In other words, help me fill up this column because we have already filled up the first column. Second column, what are the values? Can you first draw the sketch and tell me the values? This is interesting. It looks tough, but actually it's extremely easy. Can someone tell me the answers? 6EI by? Where is the I coming?
That
This is a truss element. All are zeros. All four elements in that second column are 0?
No.
No, it can't be all 0, right? Which is non-zero?
3, 2 and 4, 3 are 0.
K22 will be
3, 2 and 4, 2 are 0.
I'm sorry, all of you get 0.
this is
You see, all you have to do is to lift it up
yes sir.
like a rigid body,
Then what?
right?
But why not displace it?
That member has stiffness only along its own axis. So he gave the correct answer. All you do is to lift it up. It will move like a rigid body because you are allowing that movement, and it's pin jointed. See, the first thing you learnt was in a truss member you will have a force only in that member. There is no shear force. There is no shear force in a truss member. So how can you have a non-zero there? So I have a member like this. Please look carefully. I have a member like this. I want, for you this is left hand, right? I want this to go up. Okay. No problem. Right? This is rigid body motion. Got it? So this is something new. You got a matrix with the second row 0, and this is very easy to do. The third one. Fourth one is another set of zeros. So what does that matrix actually look like? Fill it up. It's got a lot of zeros in it. So sometimes your stiffness matrix looks like this, which is why the reduced element stiffness method said, why should I put a lot of zeros? I don't need those zeros. So it becomes smaller. Have you got the hang of this? Is this clear? This is a, but then the question is, why should we have such a matrix? How is it helping us? So we are saying di star into ki star is equal to fi star. I can have an element in a truss like this. Please listen. Please listen. I can have an element in a truss like that, which takes a shape like that, right? So certainly I have 4 values for these displacements, right? So the components of this 4 by 1 can be independent, no question about it. So this is a valid vector, the components of these are independent. But this vector, you know that it can have forces only along this direction, right? So what does that mean? Okay, by the way, this will be one value, this will be other. So this will be di1 star, this will be di2 star, etc., etc. So these 4 values can be independent. That's why we call them degrees of freedom. But these are not independent in the sense of the 4 values, the second will be 0, the fourth will be 0. And even worse, these 2 are not truly independent because the resultant of them must be aligned along this direction. Is it clear? So we will see it is related to the rank of the matrix. What is the rank of the stiffness matrix? 1. It's 1. So that you can see that this can be reduced to 1s. So all that we learnt in concepts of matrix algebra are very deeply meaningful. They have a physical meaning as well. Okay, so we need this matrix, it's helpful. We need this. We want the big picture, and no matter what we do, we should get correct results. We know that even after you multiply, you should get zeros. Obviously, if the second row and fourth rows are zeros, you will end up with zeros. You have to. So that this has a physical meaning. For a beam element, without much ado, the stiffness matrix will look like this. We will study it in depth later. You already have a clue why it will look like that. For you can take break it up into 4 parts. We will study it in detail later. Do not worry too much about it. You can fill up this matrix. Okay, here it is a function of EI. Remember 4 EI by L, 2 EI by L, 6 EI by L squared, 12 EI by L cube. That is all that you can get. If you have a plane frame element, you will have a combination of the truss and the beam. We will see this later. This is 6 by 6. Right now it is an introduction. You should know that you have these element stiffness matrices. Now the challenge for us is we have got the transformation matrix, we have got the element stiffness matrix. They are properties of the dimensions of the element, length of the element, and the E and A or E and I values. How do I get the element stiffness matrix in the global axis system? Not for the structure, I am still sticking to the element. So in the local axis system, this is what I have got. I have got Ki star. What I want is this. So you see how I am getting to do it. This di can be written as Ti di, got it, the star, right? And now if I do that, I am able to get into the global axis system, and Fi is also Ti transpose F star I. Remember, you plug this in there, you get F star I is K star di star from first principles, and when you substitute here, finally you will get it in this form. This is a standard form, this is a standard transformation we do. So this is how you are able to derive the stiffness, element stiffness matrix without the star, that is the element stiffness matrix aligned in the global axis system. Once you have the transformation matrix Ti, which you got, it is just sine and cos and maybe 1, and you have the local element stiffness matrix. This is a fundamental principle in matrices. Is this clear? Now look at this transformation. This transformation tells you this is definitely symmetric. So when you pre-multiply and post-multiply with the transpose of a matrix, you will end up with another symmetric matrix. Okay, so this is something that can be done effortlessly in the computer. So you generate the Ti for all the elements, generate the Ki star for all the elements, do this exercise, you have got straight away, you have aligned all the elements in the direction of the global axis system. Okay. To give you a parallel, you have these national parties in the central government, right, different parties, political parties, I do not want to give any names. They will all have their little groups in the state government also, they will all aligned, already aligned, they will only vote for them, right. So it is something like that, you got the groups at the state level. Okay. So let us take this one picture, is a beautiful way to understand it. I want you to draw it. I am going to draw a playground with 4 corners. Okay, at the bottom line, you see how I have done it. It is very easy to do it. I am putting the forces on the left side, the displacement on the right side, right. So the first transformation that I have is the element displacement vector in the local coordinates with the star. If I have this and if I pre-multiply it with the element stiffness matrix, I get the element force vector in the local coordinates. Is this clear? This is the meaning of the arrow. I am not writing any equations, I am symbolically showing you this first transformation. It is a linear transformation. In other words, if you give me this and I have this, I pre-multiply this with this, I get this. That is why the arrow is pointing this way. This transformation I know. Clear? What is the other transformation you know? No multiply. We are playing a game, okay? We are not writing any, deriving any equation. So this is the other one. This is aligned along the global axis system, right? So I have di without the star, I have ki without the star, and I have fi without the star. This is in global axis system, this is in local axis system. Is it clear? So both arrows point this way. This is the element stiffness matrix in the global axis system, this is the element stiffness in the local axis system. Is it clear? Then what is the other relationship I have? I have this relationship. I have this relationship from global axis system using my element transformation matrix, I get the element displacement vector, right. Now I have got this nice playground with 4 corners with these, so let us say I have this vector, can I straight away go to this vector? How? I mean I take a shortcut, I do not walk along these corridors, I just cut across straight here. How do I move from here to here? Okay, even before that, is there a relationship between this and this? Yeah, there you are. Okay, that is the inverse of the transpose. So your playground, your corridors are now ready. Now let us do the diagonal. Does this make sense to you? Is this easy to remember? Those matrices are not easy to remember. Playground is easy to remember. This is a nice sketch. I want you to keep drawing it till you master it. 4 corners are clear, and the 4 transformations are clear. They are all symmetric matrices, they are all square matrices. So are these terms clear to you? Now let us take the diagonal. How will it look? It will look like this. This is equal to this times this. This is equal to this times this. Therefore this is equal to this into this times that. That is a shortcut. Got it? Now what is this in terms of this? Just take this and pre-multiply by that, and so instead of going around along the corridors to reach here, I take a straight shortcut from there to there, and obviously it will look like that. Is it clear? This is the first of many diagrams like this we are going to draw in this course, but they are the easiest way of remembering the relationships. Okay, let us play this game once more. We began with this, then we did this, then we did this, then we did this, all 4 are crystal clear. Then we said take the shortcut from di to fi star like that, and then we said my objective is to get this in terms of all the other jokers. So from how do I do this? Straight away like that. Got it? That is all. So you have got all the relationships to do the direct stiffness method. Let us just demonstrate with one example, then only you will understand. Okay, you have got this problem, you have got 12 degrees of freedom, 8 are active, 4 are restraint. These are our element level degrees of freedom aligned in the global axis system, okay, and these are the compatibility relationships. You yourself spelt it out very nicely, and we need to do this transformation. How do we do it? Okay, I want you to see how you have got the three Ti values, you have got the 3 Ki star values, you do the Ti transpose Ki star Ti, you got the 3 Ki values. What are the Ki values? You have got the element stiffnesses The computer does it effortlessly for all the 3 elements. Now the big question is, how do you assemble the structure stiffness matrix? No, you have done that. You did that and you got this. See, take the first element. The first element, the start node is matching 10, 11, 12 of the global coordinates, and the end node is matching 1, 2, 3 of the global coordinates. So I am writing 10, 11, 12, 1, 2, 3, 10, 11, 12, 1, 2, 3, and I am saying I have already got this. I have got these. Is it clear? Do you understand the meaning of this? I have assembled this. I have assembled this K1. How did I assemble this K1? I did the transformation that we saw in the last step. I am now moving from state government to central government. I have got 3 states. All the 3 states have they have already been aligned. The stiffness matrices are ready. K1, K2, K3 are ready. How do I put up the big matrix? What is the size of the big matrix? No, for the whole structure. No, there are 12 degrees of freedom. 12 by 12. So it is like this. Please listen carefully. Listen carefully. I got my 3 elements. In this I got a 6 by 6 matrix. In this I got a 6 by 6 matrix. In this I got a 6 by 6 matrix. 3 elements. All of them somehow must fit into my 12 by 12 matrix of the whole structure. So you have to collect boxes from here and put them into the main 12 by 12 box. The right box goes to the right slot. If you do not do that, you miss out. So there must be a clever way of doing it. How do I do it? Okay, that is what I marked here. I marked here. See, I have a 12 by 12 matrix, and you can see nicely they come in packages of 3 by 3. So the big 12 by 12 I have 3 by 3, 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 and like that I have got all these slots, right. Now you just need to match these linking numbers. You got 10, 11, 12, 1, 2, 3, 10, 11, 12, 1, 2, 3. So this matrix I can make it look like this. Got it? So this is 10, 11, 12 global, this is 10, 11, 12 global. So this should go to, in the main structure, 10, 11, 12 global, it goes straight there, because stiffness is add on. You have studied this in displacement method. If I have 2 elements and the contribution of this to the structure stiffness matrix is something, and this, they add on to the joints. We have done that understanding earlier. So you got an element stiffness matrix contribution. It is like a donation coming from the state party to the central party. So it should go to the right slot. Are you clear? So this will go to 10, K10 to 12, K10 to 12. This will go to, this part is 1, 2, 3, 1, 2, 3. So this will go to 1, this will go to the upper left corner. Please listen carefully. No, this is interesting, because once you get it, you get it. See, look at this matrix. This matrix is 1, 2, 3, 4, 5, 6. Unfortunately, my start node is 10, 11, 12. And my end node is 1, 2, 3. Do not blame me for that, that is the way I did it, right. I did it because we decided that active degrees of freedom should come to the top of the list and restraint degrees to the bottom. So for my element level, the upper left corner became 10, 11, 12. I mean it was not my choice, it happened, and the lower left became 1, 2, 3, but I have to, so I make these boxes and keep it ready, right. Does this make sense? Then there is a cross from 1 to 3 to 10 to 12 and 10 to 12 to 1 to 3. Is it clear? Does this make sense to you? If it does not, go back and read up from the book. Okay, take the next slot. The next element is, this is easy, 1, 2, 3, 4, 5, 6, nothing to worry, it will go to the right slot effortlessly, no need to play around. And the last one is 4 to 6, which you need to modify because you have got a mix up of 8, 9, 7. Sometimes this happens in real problems. So you have to just rearrange the rows and columns, you get 7, 8, 9. At the end of the day, this is what you need to do. This is your 12 by 12 matrix. From the first K1 you get this, okay, so you get this, you have to appropriately put the boxes. And does this make sense to you? There will be some zeros, and this is my KAA, this is my KAR, this is my KRA, this is KRR. If you've understood, very good. If you haven't understood, not to worry, okay. We will pick up this later. This is just an introduction, we are not actually solving any problem, but we are trying to see how you can make, by proper planning, the computer do everything for you. Okay, we will carry on from this point next class. Thank you.